Hello, my name is Aaron Bouch, and I'm a field applications engineer with IAR Systems Software Company. Today I'm going to try to provide a roadmap of things to look out for when you're moving your machine learning or artificial intelligence applications from a 32-bit environment to run on a full 64-bit implementation. Of course, the first question to ask is, why should I do this? If there are downsides to moving, or even a few gotchas that might cause problems, why not just leave well enough alone? Well, to start, there are some generic answers to why you'd move that apply to almost any application. The first and not so convincing argument is, well, it's not so bad. In other words, you've got this 64-bit hardware to take advantage of. Why not use it and get some potential benefit from it? One generic benefit will be a much larger address space. This can provide performance advantages by avoiding bank switching and grouping data into smaller chunks where switching requires table lookups and other tricks. In addition, many of the most powerful but still inexpensive processor core architectures are 64 bits today. If you want to take advantage of the highest performance core microarchitectures, you're likely running on a 64-bit ARM core where the newest advances show up first. Things like superscalar execution, hyperthreading, etc., give you more instructions per clock cycle. In addition, the highest execution clock speeds are likely to show up in 64-bit A cores before migrating to embedded M core implementations. As a result, the same amount of work may be accomplished in fewer clock cycles, enabling the system to idle more and spend more time in a low power state. Ultimately, the most powerful processor may end up being the most energy efficient solution to an application challenge. In most cases, well-written code, when recompiled in a 64-bit model instead of 32 bits, will just run. So the first step can be a simple rebuild and see what happens. One thing in your favor is that the move is nowhere as bad as moving code from 16 bits to 32 bits, if any of you are old enough to remember what that was like. For one thing, when that transition happened, the rules for writing clean, non-target dependent code were not well understood and rarely observed in embedded software design. Of course, an argument of, well, it shouldn't be so bad, let's see what happens, isn't so compelling. So looking specifically at machine learning and artificial intelligence, what's to be gained? On the one hand, most AI and ML algorithms use relatively small data to represent probabilities. Even an 8-bit value can give you a resolution of 0.5% when looking at comparing the probabilities of one solution outweighing another. And when all is said and done, choosing one solution over another when one is 56% and the other is at 56.5% is unlikely to meet threshold requirements anyway. Of course, intermediate calculations will need as much precision as makes sense, but even with this in mind, most AI algorithms use 8-bit data sets, or perhaps 16 bits. However, if we look at it from a SIMD or VLIW point of view, having 64-bit registers and operations also applies to operations where many small data values can be operated on in parallel. In a 32-bit core, this generally means that you can operate on up to 4 byte values or 2 16-bit values in a single instruction cycle. In a 64-bit machine, this becomes 8 byte values at once, and likely at higher clock speeds. This can result in speedups of 2 times, 4 times, or more. And this does not even take into account the fact that many 64-bit processors will also have vector accelerators that can operate on 128 or 256 bits at a time. These could represent SIMD operations on up to 16 or 32 bytes at a single time, again multiplying your throughput by another factor of 2 or 4 over the 64-bit core register operations. Then there's the question of address space. While it's true that for many microcontroller embedded applications, the thought of 2 gigabytes feeling small seems ludicrous. In the case of machine learning datasets, however, this can be an exception. When creating datasets for an AI engine to compare many solutions to determine what it's looking for, the more possible answers it's aware of, the finer the results can be. This means that datasets can grow exponentially without you even noticing. And removing the constraints to be concerned of how much data is being used as memory gets cheaper and cheaper can be a real benefit in these applications. And of course, the more things you have to compare, you get back to the first point that crunching all of this data takes a massive number of calculations and instruction cycles, making the higher performance available in 64-bit architectures even more important. Okay, so you've decided to take the plunge and try to move your application to 64 bits. Let's look at the things that you want to look at in your existing code, assuming it doesn't just run out of the gate. While the concepts of changing sizes of fundamental data types is similar as when we went from 16-bit machines to 32 bits, the impact should be much smaller. Regardless, as you can see, there are many specific things to look for in your code to be ported that could present problems. And the worst are the ones that don't present themselves immediately as issues. The key thing that must be carefully analyzed are the differences between the 32-bit and 64-bit data models and pointer sizes. For example, the basic meaning of some data types, which were all 32 bits before, will now possibly be interpreted where some are still 32 bits and others are now 64 bits. Where integers were 32 bits and still will be, long integers, which were interpreted as 32 bits before, will likely represent 64-bit data now. If your code arbitrarily mixed these since bigger is better and it's the same thing anyway, there may be some surprises lurking when you rebuild. Also, casting from one type to another, particularly where pointers are involved, which used to be quite simple since everything was 32 bits anyway, now need to be looked at quite critically. This graphic gives an overview of different data models and how they treat different data types and objects in your code. The letters represent the different data types, where I is an integer, L is a long integer, LL is a long integer, P is a pointer. And just for completeness, S represents a short integer and only shows up once. On the second line of the table, you see IP16 L32. This means that integer and pointer values are represented as 16 bits, while longs are 32-bit values. A common 16-bit architecture reference from the past, one we probably all want to forget. Going down a few more lines to just above the heavy line indicating crossing into the 64-bit territory, you have ILP32, LL64, meaning integers, longs, and pointers are all represented by 32-bit values, and long integers are 64 bits in size. This should be familiar to most programmers working with 32-bit ARM processors today. Then you cross over, and now things change. You have IL32, LLP64, where integers and longs both remain 32 bits, and longs and pointers are 64 bits. Or the more common I32, LP64, where integers remain 32 bits, but longs and pointers are now 64 bits. This is the model that we'll be focusing on today. Because of this, the principal cause of problems when converting 32-bit applications to 64-bit applications is the change in size of the int type with respect to the long and pointer types. When converting 32-bit programs to 64-bit programs, only long types and pointer types change in size from 32 to 64 bits. Integers of type int stay at 32 bits in size. This can cause trouble with data truncation when assigning pointer or long types to int types, and also problems with sign extension can occur when assigning expressions using types the size of an int to an unsigned long or a pointer. C integer types and the floating point types are the same in both data type models. However, it is not unusual for current 32-bit applications to assume that the int type, long type, and pointers are all the same size. Because the size of long and pointer change in the LP64 data model, this change alone is the principal cause of ILP32 to LP64 conversion problems. Since plain integers and pointers are the same size in ILP32 compilation environment, 32-bit code commonly relies on this assumption. Pointers are often cast to int or unsigned int for address arithmetic. You can cast your pointers to unsigned long because long and pointer types are the same size in both ILP32 and LP64 type data type models. However, rather than explicitly using unsigned long, use uint ptr underscore t, or unsigned integer pointer type, instead, because it expresses your intent more closely and makes the code more portable, insulating it against future changes. To use the uint pointer underscore t and int pointer underscore t, you need to include the file inttypes.h. Consider the example shown. We have a pointer to a character, p, and p is equal to the cast of character pointer, integer p, and page offset. Now, the compiler may give you a warning saying that conversion of pointer loses bits because you're converting a pointer to an integer, which is smaller when you're in the 64-bit model. The following version will function correctly when compiled to both 32 bits and 64-bit targets by replacing the integer representation with uint pointer underscore t cast to p and page offset. Here, by using an explicit pointer type, all works regardless of what model you use, and it's easier to tell the intent of the programmer. Because integers and longs are never really distinguished in ILP32 or 32-bit data type model, your existing code probably uses them indiscriminately. You'll want to look for and fix any code that uses integers and longs interchangeably so that it conforms to the requirements of both the ILP32 and the LP64 data type models. While an integer and long are both 32 bits in the ILP32 data type model, a long is 64 bits in the LP64 data type model. Consider the example shown. We have integer waiting and then long w underscore io and long w underscore swap. And then we have the line that says waiting is equal to w underscore io plus w underscore swap. Now, the issue you have here is that when this is compiled with a 64-bit compiler, you get a warning saying that a 64-bit value, which is calculated when the two longs are added together, is truncated when assigned into the integer value waiting. In the 32-bit model, these were all 32-bit entities and all's fine. but moving to 64 bits changes the meanings, possibly resulting in truncation and loss of data. This can be most incipient in that your data may work such that the values never exceed 32 bits, or only rarely in some unusual conditions. In this case, the code may work in spite of the truncation most of the time, but present a latent bug waiting to bite you in the field. This is a good example of why every warning generated by the compiler should be read, understood, and if possible fixed when they occur. You can't compile with errors, but warnings are just warnings, right? They can just be ignored. Well, not so fast. Sign extension is a common problem when you convert to the 64-bit compilation environment because the type conversion and promotion rules are somewhat obscure. This was a major source of issues in the move from 16 bits to 32-bit code, and again rears its ugly head. To prevent sign extension problems, use explicit casting to achieve the intended results. To understand why sign extension occurs, it helps understand the conversion rules for ISO-C. They're a little bit odd, but understanding them helps, and even more, understanding what to do to avoid problems is very important. The conversion rules that seem to cause the most sign extension problems between the 32-bit and 64-bit compilation environment come into effect during the following operations. First is integral promotion. You can use a character, short, enumerated type, or bit field, whether signed or unsigned, in any expression that calls for an integer. If an integer can hold all possible values of the original type, the value is automatically converted to an integer. Otherwise, the value is converted to an unsigned integer. In other words, in the background, with you not even knowing it, the compiler with valid C operations may convert your values into integers, which are signed values, when you never intended that in the first place. And then we have the rule that says conversion between signed and unsigned integers. That when an integer with a negative sign is promoted to an unsigned integer of the same or larger type, it is first promoted to the signed equivalent of the larger type, then converted to the unsigned value. This means that the value will first be sign extended. So if the MSB was a 1, since it's negative, the new bigger value will be filled with 1s in the upper half of its bits. When the example shown is compiled as a 64-bit program, the ADDR, or address variable, becomes sign extended, even though both ADDR and A.base are unsigned types. So we have this structure foo, in which case it contains an unsigned integer base and a value rehash in that structure. Then we instantiate a structure A, and look at the element A.base, which is unsigned, and we assign it to address, which is also unsigned, A.base with a left shift of 13 position. The problem is that because of the C rules, this is going to get sign extended. We then print that, and then print the same thing but without the sign extension operation. So the sign extension occurs because the conversion rules are applied as follows. The structure member A.base is converted from an unsigned int bit field to an int because of the integral promotion rule. In other words, because the unsigned 19-bit field fits within a 32-bit integer, the bit field is promoted to an integer rather than an unsigned integer. Thus, the expression A.base shift left 13 is of type int. If the result were assigned to an unsigned int, this would not matter because no sign extension has yet occurred. The expression A.base shift left 13 is of type int, but it's converted to a long and then to an unsigned long before it's being assigned to address. Because of signed and unsigned integer promotion rules, the sign extension occurs when performing the int to long conversion. Thus, when compiled as a 64-bit program, the result that it prints out first as the value for ADDR has FFFFs in the upper half of the value, and then 8000 with zeros after it. And then the second time it prints it just as 80000000, which is what you wanted in the first place. However, when compiled as a 32-bit program, the size of an unsigned long is the same as the size of an int, so there's no sign extension, so both representations of the variable print out the same as hex 80000000. It's always good policy to define structs or structures in such a way that element sizes go from largest to smallest. In this way, there will be no need for padding or gaps in the data storage for the structure. This is because each data element is generally aligned on its natural size boundary. So if you have a byte value followed by a 64-bit value, the byte value will be padded to the next 64-bit address boundary, adding 7 bytes to the storage footprint. Here we show a struct with a mix of integers, longs, and a pointer. When built with a 32-bit compiler, these are all 32-bit types, so the order is irrelevant. However, when built with a 64-bit compiler, the pointers and longs become 64 bits, forcing the 32-bit values that precede them to be padded, adding an extra 8 bytes of storage to each instance of this struct. The second example has the same data but ordered so that all of the 64-bit values come before the 32-bit values, resulting in no padding and the most efficient use of memory when instantiating this struct. Unions are a very useful and powerful tool to view a set of bits in memory in different ways. For example, an unsigned integer might be useful when accessed as a full 32-bit value in some cases, but you may also want to access the individual bytes separately for other data manipulation operations. Similarly, defining a register as both a full set of 32 bits, as well as individually accessible bit fields, can be essential in embedded control of peripheral registers. Be sure to check the members of unions because their field sizes can change between the ILP32 and the LP64 data type models, making the size of the members different. In the union example shown, member underscore D and member score array underscore L are the same size in the ILP32 model, but different in the LP64 model. This is because long types grow to 64 bits in the LP64 model, but double types, the floating point types, do not. So we have the typedef union double underscore T and long underscore L with an array with 2 elements. The size of the members can be rebalanced by changing the type of the underscore L array member from type long to type int, or better to int 32 underscore T, which always has the same meaning regardless of data model used. Of course, in this case, we're looking at the bits of a floating point value as separate integer numbers. In reality, a signed integer is probably not what you would use anyway. Instead, you would likely want to use unsigned values, where you can expose the underlying fields of the floating point data, such as mantissa, exponent, and sign, separately. Another area to be careful about is how constants are interpreted by the compiler. Here again, good coding practices in the 32-bit model can avoid issues when compiling in a new data size model. A lack of precision can cause the loss of data in some constant expressions. Be explicit when you specify the data types in your constant expression. Specify the type of each integer constant by adding some combination of either lower or upper U or lower or uppercase L. You can also use cast to specify the type of a constant expression. Consider the following example. where integer I is set to 32, and then you have long of j equal to 1, and that's shifted left by I, or 32 positions. In this case, j will get 0 because the right-hand side is an integer expression. 1 gets promoted to an integer even though you probably intended it to be unsigned. So the above code can be made to work as intended by appending the type to the constant 1, such as 1 with a large L. This also exposes another assumption in the C language that's often missed and can be avoided if you simply are explicit when using constant expressions. C will promote all values to a signed integer when not instructed otherwise. Therefore, when you have a constant expression when a value intend to be unsigned, like an absolute address or a bit field representation, it's always good to append a small or large u depending on the size of the field you want. When using file and string I/O operations, taking care that the variable sizes still line up correctly can be quite important. Make sure the format strings for printf, sprintf, and scanf, and scanf can accommodate long or pointer arguments. For pointer arguments, you can use the format string %p to work in both the 32-bit and 64-bit compilation environments. For long arguments, the long size specification L should be prepended to the conversion operation character in the format string. Also, check to be sure that the buffers passed to the arguments in sprintf contain enough storage to accommodate the expanded number of digits used to convey long and pointer values. For example, a pointer is expressed by 8 hex digits or 8 bytes, ASCII bytes, in the ILP32 data model, but expands to 16 bytes in the LP64 data model. And finally, check to be sure that buffers used by sprintf contain enough storage to accommodate the expanded number of digits used to convey long and pointer values. For example, a pointer is expressed by 8 hex digits in the ILP32 data model, but expands to 16 in the LP64 data model. A buffer that fit the resulting string before may overrun in some cases, causing all kinds of unpredictable behaviors depending on what data is in the adjacent memory. One good rule of thumb to consider is that for data structures that are shared between 32-bit and 64-bit versions of an application, stick with data types that have a common size between ILP32 and LP64 programs. Avoid using long data types and pointers if possible. Also, try to avoid using derived data types that change in size between 32-bit and 64-bit applications. For example, many types defined in sys/types.h change in size between the ILP32 and the LP64 data models. This includes clock_t, which represents the system time in clock ticks, dev_t, which is used for device numbers, off_t, which is used for file sizes and offsets, ptrdiff_t, which is the signed integral type for the result of subtracting 2 pointers, size_t, which reflects the size in bytes of objects in memory, ssize_t, which is used by functions that return a count of bytes or an error indication, and time_t, which counts time in seconds. Again, this is often the difference in interpretation of integer versus long variables between the two data types. Using the derived data types in sys/types.h is a good idea for internal data because it helps to insulate the code from data model changes. However, precisely because the size of these types are prone to change with the data model, using them is not recommended in data that's shared between 32-bit and 64-bit applications, or in other situations where the data size must remain fixed. Nevertheless, as with the size of operator discussed before, When making any changes to the code, consider whether the loss of precision will actually have any practical impact on the program. For binary interface data, consider using the fixed width integer types in int types.h. These types are good for explicit binary representations of all of the following types: memory data, over-the-wire data, hardware registers, and binary data structures. These data types keep their size and sign characteristics regardless of what data model is implemented in a given compiler. Being aware of how your selection of data types affects what actually happens in the processor implementation can be very important. Many modern 64-bit ARM cores use cache memory to enable the CPU to run at full speed when data instructions are in the cache, but suffer severe penalties in performance of between 2 times and 10 times slowdowns when data must be accessed from the next level of memory, even if it's on chip. This can cause large arrays of long or unsigned long types to cause serious performance degradation in the LP64 data type model as compared to arrays of int or unsigned int types. Large arrays of long types can cause significantly more cache misses and consume more memory. Therefore, if int works just as well as long for the application purposes, it's better to use int rather than long. This is also an argument for using arrays of int types instead of arrays of pointers. Some C applications suffer from serious performance degradation after conversion to the LP64 data type model because they rely on many large arrays of pointers. Again, using these types interchangeably in a 32-bit architecture is common, and no difference is seen in how operations occur. However, when moving to a 64-bit model where some data types double in size, keeping these values in memory can significantly affect both memory utilization and cache behavior and performance. It's easy to make an error in the code while working with separate bits. The following error type relates to shift operations, and here's an example. We have a pointer difference type set bit and pointer diff type value. So this code works well on a 32-bit architecture and allows you to set bits with numbers 0 to 31 to unity. After porting the program onto a 64-bit platform, you'll need to be able to set bits 0 to 63, but this code will never set any bits above bit 32. Again, we need to be aware that C treats the constants expression 1 as a signed integer type, and when a shift of 32 positions occurs, an overflow will take place, as shown in the figure. Whether we will get 0, as in section B before, or 1, as in section C, as a result depends on the compiler's implementation. Section A shows correct setting of the 32nd bit and 32-bit code. Sections B and C show an error of setting the 32nd bit on a 64-bit system with 2 different ways of behavior. To correct the code, we need to make 1 constant of the same type as the mask variable. So we can do this by having a cast of pointer difference underscore t of the 1 shifted by the bit numbers. Also note that the incorrect code leads to one more error. When setting 31 bits on a 64-bit system, the result of the function will be the value FFFFFFF 8,000,000, where the upper bits are set to 1 to sign extend the value. The result of 1 shifted left by 31 expression is the negative number minus 2 billion something. In a 64-bit integer variable, this number is presented as all F's, then a single bit followed by all zeros. Not what you expected or wanted. Once more, a good argument for being explicit in your definition of constant expressions in any data model. Magic constants, that is, numbers which are meant to represent the size of this or that type, can cause a lot of trouble. The proper decision would be to use the size of operator for these purposes, but in a large program, an old code section can still be hidden, whereas programmers believe the pointer size is 4 bytes, and in size T, it's always 32 bits. Usually such errors look like the code shown in the slide. The figure shows the basic numbers, which you should be cautious working with while migrating onto a 64-bit platform. And the table shows basic magic values, which are dangerous while porting applications from a 32-bit platform into a 64-bit. So we've looked at some very common programming practices that seem to cause no problem when working within an environment where many data types have the same size, that is 32 bits, but can really hurt when moving to a data model where longs and pointers are now 64 bits. The question is, as I go through my code to find and fix these issues, how can my toolchain help? When making the migration from 32 bits to 64 bits, it's important to consider the fact that not all tool chains are created equal. Some will help you see the differences of how your code is interpreted when changing from one data model to another. Here are a few key things to consider when moving your code to a 64-bit environment and toolchain. First, look at the libraries that you're using. Some may be internally developed and need to be rebuilt using the new model. This is straightforward, but must be done. Are you using outside and third-party libraries? These may not work with the new data representations and may need to be changed to different libraries if the third party has even rebuilt them. Of course, you'll need tools with true 64-bit compiler and assembler support. But then does this extend to the debugger you use? Is it aware of the differences in disassembled code when working in 64-bit mode versus 32 bits? Can it automatically switch watch window displays based on the context of the code? There isn't much more to say about the importance of having a 64-bit compiler other than you must have one. Give preferences for tools that can support combined 32-bit and 64-bit core solutions to facilitate your multi-core development and resource optimization. Today, many single chips have multiple cores. You may have a 64-bit core complex with 1, 2, 4, or even more identical cores running as an SMP cluster. In addition, you may have one or more other cores running dedicated functions, such as real-time I/O control or functional safety processing. These will likely be 32-bit cores. It's important that you can develop code for the different cores, whether they be 32 bits or 64 bits, with the same tools. Also, as more and more applications require some kind of functional safety certification, whether it be for industrial, medical, automotive, or just because designing this way produces more reliable and robust end products, it can be important that your tools are available in a functional safety version so that upgrading can be smooth and simple when needed. And don't forget that using a large amount of assembler code can significantly increase the cost of porting to the 64-bit version of an application. Some tools don't even support 64-bit inline assembler code. Of course, it's good practice to try to minimize assembly code, both inline and in separate source files as much as possible. Consider rewriting some of the assembler modules in C or C++ for future-proofing your code. Quality commercial tools will provide either built-in or library functions that can be used in your C and C++ code that provide many of the functions you're using your assembly routines to access. Using these instead of assembly language can greatly enhance portability, whether it's for moving from 32 bits to 64 bits or from one architecture to another. As noted before, many 64-bit chips contain multiple cores, either in SMP clusters, as separate I/O processors, or both. Since the end system's complexity will naturally increase as you utilize these valuable resources, debugging a multi-core system can be quite difficult without the right tools. When you have one project running on your main processor, which may be a 64-bit core or SMP core complex, and a different project running on another core, providing I/O services or safety services to the system, being able to view both projects at the same time in the debugger, observing behavior or multiple systems, and ideally being able to stop or start one core based on something that happened on the other is critical for debugging those complex synchronization issues. The days of writing code, running it, and seeing if it all just works are long gone with these kinds of complex systems. Also, having a software simulator available as part of your execution environment can be critical. This is true because 64-bit boards can be much more expensive than their 32-bit core brethren. But also, when building unit testing frameworks, you often will want to test code fragments in a pure software environment without tying up valuable hardware resources and debug probes. Humans make code updates. It's something that somehow escapes the notice of planners at some organizations, but it's a fact that you need to consider. If your coding team lacks 64-bit program experience, it presents a barrier to performing an application upgrade. For example, team members should be aware of the rules for converting data from 32-bit to 64-bit and vice versa. What's worse is that these rules are generally unwritten, platform and application specific, and often rely on past experience. If you have any hiring responsibility, ask job candidates about their experience in this area. If you're just a programmer and can only deal with the people you're dealt, pay even more attention because it's knowledge you need to acquire, and it won't be bad for your career if the 64-bit expert turns out to be you. If team members lack this sort of information, the resulting 64-bit application will likely contain errors that the team won't even find. More importantly, the lack of 64-bit programming skills will cost time and money, something in short supply for most organizations today. Hopefully, the discussion today can act as a template for the sorts of things to look out for if you or your team members have lots of experience using 32-bit processors, but are considering increasing your expertise and experience to include building and porting code for 64-bit processors. So let's summarize what we've talked about today. First, as motivation, it's fairly clear that there are some big wins in performance, power savings, and simplification that can be achieved in machine learning and artificial intelligence powered applications by moving to 64-bit devices and a 64-bit programming model. We've touched on a number of things that should be looked at carefully when moving code from a 32-bit environment to a 64-bit platform. While at first impression that can look large, they fall into a few categories that can lead to improvements in your code that will make it better and more reliable even in the 32-bit world where it started. And finally, when making this transition, it's important that you choose quality tools that can help you quickly zero in on areas of concern and debug problems rapidly, saving time and money in the process. As you can see, this is not the first time these questions have been tackled. Here are a few good reference sources for more reading on the topic of moving to 64-bit processors. And finally, thank you kindly for spending some time with us today to look at this topic. I hope you've gained some useful perspective and that this makes your development more successful.